Good evening, distinguished professor, colleagues, and guests. My name is Sarheldan Bakki. I am honored to present my research titled Produced Water Desalination Using Functionalized Cellulose Acetate Membrane. This of my master's study at the Institute of Science and Modern Technology, Rojava University. As we all know, environmental pollution remains one of the greatest global challenges. Among the major contributors is the oil and gas industry, which produce a waste stream known as produced water. As we know, produced water is a complex mixture of formation water, hydrocarbons, injected water, and treatment chemicals. For perspective, the production of a single barrel of crude oil can generate up to 10 barrels of produced water. If this water not treated properly, this water can cause severe environmental and health hazards. This pollutant water has potential impact on the environment in case of aquatic life, human health, and soil and air, etc. So the objective of our study is to, to develop an eco-friendly, high-performance membrane for produced water desalination. Sorry, because my net is not that good. So this approach, to achieve this approach, we incorporated silicon nanoparticles derived from agricultural waste into cellulose acetate membrane. This approach not only improves membrane performance, but also contributes to sustainability by using low-cost and renewable resources, such as corn cob,
Sarheldan.
which we used in our study.
Sarheldan.
The methodology of our work.
Sarheldan.
Okay,
ممكن تكبري الشاشة، تدوسي اللي هو التكبير سلايدز لان هي صغيرة. سلايد شو.
اوكي. المشكلة عندي النت ضعيف شوي، عم بيتأخر حتى عم بيطلع.
تمام كده، جميل. والصوت حاولي تعليه شوية.
اوكي. Our methodology involves three main steps. First step was the preparation of corn cob ash from the corn cob. The process was first collecting, washing, drying, burning, and finally ash obtaining. After we obtain this ash, we use this ash to obtain or to extract silicon nanoparticles. So the third step was synthesis of silicon nanoparticles through sodium silicate solution, which is clear here. We take 20 gram of CCA treated with hydroxide, sodium hydroxide, and after that we treated it with sulfuric acid to obtain the silica gel at pH 2. After that we add hydroxide ammonium to precipitate the silica at pH 8. Finally, we get the gelation and to centrifuge at with washed with hot water at 45 Celsius. After that, we filtered and dried it in an oven at 100 Celsius for 2 hours. Finally, we obtained the final product of our process was silicon nanoparticles, which we use to prepare the membranes to use that for desalination of produced water. The third step was preparation of the membranes. We prepared 4 samples of membrane with different amounts of silicon nanoparticles. First, we took the silicon nanoparticles, different amount of silicon nanoparticles, and mixed with the solution, polymer solution of cellulose acetate. We mixed it for 8 hours and left the solution for 24 hours in order to remove bubbles from the polymer solution. After that, we cast these solutions on, we casted, we cast these solutions to obtain the membrane film. After we obtained the membrane film, we immersed it a water bath. Finally, the membrane film was obtained. This membrane films was mixed matrix membrane designed to combine the best properties of the inorganic and organic materials. So our experiment was focused on mechanical properties, water flux, salt rejection, pH effect, pressure effects, and folding resistance for this membrane. This table shows a different amount of silicon nanoparticles which we used to prepare or to fabricate the membranes. It's ranged from 0 to 0.100%. This schematic diagram of the produced water desalination process, which we used in our study. The results we get after we use these membrane samples for the desalination of produced water, it's clear that increasing of the silicon nanoparticle decrease the mechanical properties or mechanical strength of the membrane. But we note that the overall performance of the membrane increase. On the other hand, increasing the silicon nanoparticles increase the water flux. As we see here for the membrane R, which contain 0.07% of silicon nanoparticle, it was about 15 LMH. And after we add the amount of 0.1% to the solution, the water flux increased to 16.09 LMH. It's clear that the silicon nanoparticles content increase or improve the water flux for the membrane. This chart shows that the rejection mechanism of the membranes was based on the repulsion charge and molecular seeding. As we see here, the membrane R4 shows the greatest efficacy of removing the salt. The salt removal order was chloride, potassium, sodium, and calcium, but the last one. So we notice that the membrane R4 is the optimal membrane to be used for more investigation on and test. Here, we took the membrane R4 to more investigation. We studied the effect of pH on membrane R4. As we see here, the pH levels can affect the rejection of salts through the membranes. But as we see, the pH at the pH 7, it was the best efficiency of the removal. We can say that the membrane surface charge, it can affect the salt rejection efficiency across the different pH level. It was clear from this chart. After that, we studied the effect of pressure on R4 water flux. We used many with pressures ranged from 8.62 to 24 bar. As the chart shows that the increasing the membrane, increase the water flux, and increase the removal of the salts in the water. So we can say that the pressure increasing can affect the removal positively. So we can say if we increase the pressure more than 24, it's the efficiency of the membrane will increase slightly. After that, we test the fouling of the membrane R1 and R4. We see that the membrane R4 performs better than R1. As we know, a membrane R4 contain silicon nanoparticles amount 0.100%. It's clear that R4 recovers more of its filtration efficiency up to 41%, and R4 has lower reversible fouling, meaning it's more durable over time. So we can conclude that the incorporation of silicon nanoparticles in the polymeric solution, Cellulose acetate, can improve the efficiency of the membrane and can give the best rejection of salts. To conclude, we can say that silica is the use of silicon nanoparticles from agricultural waste can not only enhance the performance of the membrane, also promotes environmental sustainability by utilizing renewable resources. As we say, it's we talk about the environmental pollution. We say that produced water is pollutant. This current cup is also pollutant if we don't treat it. So we use it for this study to make a green resource for the silicon nanoparticles or for the nanoparticles. We can recommend for the future studies applying a multi-stage membrane system to enhance the removal efficiency, incorporate different nanofillers to enhance the mechanical properties of the membrane, and for the mechanical properties of the membrane and the separation of salts to this process. Finally, I would
Thank you, sir. Thank you, Sarheldan. Any questions? Okay, thank you, Sarheldan.